Chapter 8, Part 6, Addition to Alkynes and some synthesis practice. So the electrophilic addition of bromine and chlorine to alkynes is very, very similar to the electrophilic addition to an alkene. The only difference is that we have two pi bonds, and so we're going to end up with an alkene product instead of an alkane. It's also interesting to note that the electrophilic addition of a halogen to an alkene is an anti-addition, and when you do the same reaction with an alkyne, it's a trans addition, which is the same thing, but across a double bond. So that's the format you're going to follow here. And then if you react with another equivalent of halogen, you can end up with a tetrahalogen product. So let's take a look at this first practice problem. We have an alkyne. We have 1 mole of bromine. So we just have to draw a product of the same number of carbons and the trans addition of a halogen. So go ahead and take a second and draw out the product on your own. Okay, pause if you're not ready. But with an alkyne, it's really important that you count the carbons. So I'm going to go ahead and label those just so you can see where I'm getting my answer from. So there are 7 carbons. Now the double bond is between carbons 5 and 6. And I know that I'm going to have an anti-addition of bromine across carbons 5 and 6. And then carbon 7 should still have an alcohol group coming off of it. So this is my product. Let's take a look at the addition of a halogen acid to an alkyne. This is, again, a Markovnikov addition. So even though we have an alkene as our product, we want to make sure that the hydrogen atom goes to the less substituted, so that we end up with the more substituted halogen. And then if you were to add another equivalent of halogen acid, the hydrogen atoms actually end up on the same carbon, and the halogen atoms end up on the same carbon. So let's do a practice problem. So same process as last time. Make sure that you are counting your alkyne. And again, when I'm numbering these to draw my products, I'm not necessarily numbering for naming. Now that I'm looking at this one, I realized on the previous page, I just numbered from left to right, and I didn't explain that that would not be how you would number that for naming. I was just making sure that all my carbons were there. So this time I'll number from right to left, which is how you would number it for nomenclature. So we have 6 carbons total. And I'm going to go ahead and draw my alkene with, without indicating like any sort of cis and trans, because it's on the end of the chain, so there is no cis or trans anyway. But the halogen, the hydrogen atom would be added here, and the halogen would end up on the more substituted carbon. And remember, there's another hydrogen here already, but whoops. And you can do this also anti-Markovnikov by adding in peroxides. So in this case, you end up with the bromine on the least substituted carbon, same as if you had done this with an alkene. You can also do oxidative cleavage of alkynes. It's even simpler than it was with the alkenes. If you cleave an alkyne, you end up with a carboxylic acid, no matter what. Notice also this is not a reductive cleavage. We're only looking at oxidative. These are different workup conditions following ozone. Okay, so on last video, last chapter, the last video included an introduction to organic synthesis. So I'm just going to remind you of some information from that. There are two types of reactions, really, if you look at organic chemistry as a whole. You have reactions that convert one functional group into another, and you have reactions that form carbon-carbon bonds. When you are working out a synthesis problem, your approach should be to first count the carbons in the target product and in the starting materials and do a comparison. Do we need to add or lose carbons? How many? Will we need multiple equivalents of the starting material? And then compare the functional groups that are present in the product versus those in the starting materials. Lay out all of your possibilities for making the final functional group. Usually working backwards can really help you because the final functional group typically only has a handful of ways that you can make this. And this process is called retrosynthesis. So let's work on a practice problem. It says synthesize this compound that's all single bonds from a compound that contains an alkyne and any other necessary reagents and carbon sources. So this is giving us permission to bring in other molecules that contain carbon. Sometimes the directions will say all carbon atoms must come from starting material, or all carbon atoms must come from, and then give some specific compounds. But this one is giving us pretty much free reign. So the first thing that I would do is count the carbons. So I would kind of ignore the cyclohexane ring because it's obviously not changing. But our final product has 1, 2, 3, 4, 5 carbons coming off of it. And our starting material only has 2. We also have to figure out how to get rid of our alkyne. So that's probably going to be a hydrogenation. Now, thinking about this, there's really only one carbon-carbon bond forming reaction that you know of right now, and that's to use a carbon as a nucleophile. Fortunately, we were given a terminal alkyne, and we know exactly how to turn that into a nucleophile. And so this one is actually pretty easy to work forwards if we want to. So we can deprotonate using sodium azonide to create a carbanion, an alkynide ion. Then we can add our 3 other carbons that we need using an alkyl halide. This gives us an alkyne with a slightly longer chain coming off of it. Now we just have to figure out how to reduce the alkyne to the alkane, and we could do this with an excess of hydrogen gas and pretty much picking our favorite transition metal. So maybe let's go with like palladium. And if you really want to help it out, adding heat can help make that go faster. Okay, let's take a look at this practice problem together. This one's a little more complex, but I think we can do it. The number of carbons is not changing between the 2 molecules, but what is the functional group and the location of the functional group. So notice that the functional group is an alcohol here, and it's moving from the secondary carbon to the tertiary carbon. So what this tells me is that at some point a carbocation has to be formed. So let's think about this. How would we make the tertiary alkyl halide? There's one way that I can think of to do that, and that would be to have an alkene reacting with HBr. So now that we know that, is there a way that we can get from here to here? Go ahead and think for a second. And hopefully what you come up with is yes, there is definitely a way to do that. That was the previous chapter. That's acid catalyzed dehydration. So we can add something like concentrated sulfuric acid and heat it up, maybe to like 100 degrees or something. That would give us our alkene, and then adding in hydrobromic acid would give us our tertiary alkyl halide.